Lesson 21 is on free body diagrams. Very important to be able to draw a free body diagram. A free body diagram is very simply a sketch that shows you all the forces acting on a specific object. So, for example, as I stand here in front of the smartboard, there are two forces essentially acting on me. As long as I'm stationary, there is the gravity pulling me down, and of course there must be something pushing me up, which is the ground. The ground is pushing me up, and those forces must be equal and opposite. Otherwise, I would be accelerating either up or down if one of them was greater than the other. And so a free body diagram is just the free body diagram in the situation will be this. You just generally draw a box to represent the object, and then you're going to say Fn, which you will learn is the normal force, and Fg, which is the gravitational force. Now, let's say that this is let's say that I've got a box on the ground and I'm pushing the box in that direction. Then you have two more forces acting on that box. You are going to have, well, for starters, you can have the same two forces which I just discussed. You can have the gravity going down. You can have the normal force going up. They should be the same size. Oops. But now since you're pushing the box, and you're pushing it to the right, you have an applied force going to the right. And of course, the opposing force of that, because we live in the real world, not a frictionless world, is you have friction. Friction always operates in the direction opposite the direction of motion. So now you have a friction force going this way. And so there's a free body diagram for pushing a box on a floor, across the floor. And actually, my applied force should be bigger than my friction force if the object is accelerating. If the object is not accelerating, then they're going to be the same size. And we'll discuss that further as we go on. So here we go. You can read over the notes. There's example 1. We just did that here. And then here are the forces that you need to be aware of, and their abbreviations. Fg, force due to gravity. Fa, the applied force. Ff, the force due to friction. Ft, the force due to tension. For example, if you're hanging a picture from a string or something like that, or a sign hanging from a roof, or if you've got, you're swinging something that's attached to a string, that's the force of tension. And then you've got the normal force and the net force. And just note that the normal force is just an N, and the net force is an NET. Okay, so here we go. We'll do a bunch of examples, free body diagrams. And you're going to be tons of free body diagrams for this unit. Sketch a free body diagram of a laptop sitting on a table. So this is really easy. We've done one already. It's just sitting there. It's not accelerating in any direction. So you've got the normal force pushing it up, and you've got the gravitational force pulling it down. I've tried to draw the vectors the same size, because they're equal and opposite, and therefore the object is not accelerating in either direction. And I'm emphasizing the word not accelerating. It could be moving at a constant velocity in either direction, and those forces would still be equal, right? Which is not intuitive and should probably mess with your head a little bit. As we go through this unit, you'll understand why that is the case. Okay, so there it is, number 3. Number 3, we got a box. What's this? You're trying to push a box across a heavy floor. Okay, so we've done this one already. Let's go to example number 4. Example number 4 says a sled is sliding down a sloped hill. Sketch a free body diagram of the sled. So here's a sloped hill. Here's a sled, and we're just going to draw it as a box. What forces are acting on this? Okay, so first of all, there's always gravity, and gravity is always straight down towards the center of the Earth. Now, in this case, the normal force is different, because now we're going to talk about the normal force. The normal force, Fn, is always, and then you've got this symbol here, and that symbol there, looks like an upside down T, is the symbol perpendicular. In other words, at a 90-degree angle, is always perpendicular to the surface. So the normal force in this case, in green, here's the surface, and it's perpendicular. So the normal force is actually going in this direction, Fn, right? It's perpendicular. It forms a 90-degree angle, there with the surface. All right, so remember this means perpendicular. There we go. Okay, now what other forces are acting on this? Well, we are going to assume, it says you have to, so we're going to have to assume that you just put the box on the slope and it's going down. So what's pulling it down the hill? That's an applied force, but in this, unless you're actually pushing with your hand, in this case, it's actually a component of gravity. For now, hold it, we're just going to close this. So the force that's pushing it down the hill is a component of gravity. Now, for now, we're just going to call it an applied force. So the applied force is going down the slope, and it's perpendicular. Sorry, it's not perpendicular. It's parallel to the slope. And then, of course, we have the force of friction, which is going to be going up the slope. Okay, so there's a free body diagram for that sled going down the hill. And note, as a point of interest, if I was pushing the sled up the hill, I'd still get my normal force going this way, still get my force of gravity going this way. But if I'm pushing it up the hill, then my applied force is in this direction. And now my force of friction is in this direction, because the force of friction is always opposite to the direction of motion. Right? So they reverse if the object is going up the hill. Okay, and that concludes lesson 21. On to lesson 22, which is applying what we learned so far.